Class is over. What? Who's in the chat? Who's in the chat? Mubot's in the chat. Mubot never fell asleep. What was this 2 months ago? 3 hours study with me. Man, I wish I could. I should just start a channel I can study. Man, getting work done. Man, start a channel called I Can Study and just do work. Get millions of views. Maybe I should just post that. I should just do an experimental video. Just look at all the top videos. Okay, dokie. Let's jump into this. What do we have? We do have some assignments. Chapter 15. But we have on the 15th the confidence interval for the mean. I think this is the quiz. Let's try this. Might just do every single question. Every single question. Let's jump into this. Here we are. We're going to do a lot of questions right here. This question, let's mark it in the video. I marked it in the videos, right? I'm so tired. Why? Okay, here we are. 313. Step 1. Chapter 4. What's up, Peyton? What do you want to do, Peyton? Have you done the quiz? Confidence interval. Wait, chapter 14. We know what it is. And then using the t-table. What's really good, if you've done a bunch of these, you can actually figure out a lot of these values. We're going to right now, what's your question say? Tell me what your question says. Let's just jump to it. 2.6. And this one is 2.05. Got it. A study looking at the annual compensation rates. You got it. So if anyone's wondering how I got this question right here, and then we're gonna jump to Peyton's. With this question right here, you want to use the t-applet. And I'll explain how I was able to solve this, and then we're gonna jump to Peyton's question. But with the t-applet right here, the first thing you enter into the t-applet, and I'll put it side by side on the screen, but you're gonna enter in the degrees of freedom. The degrees of freedom. So with the degrees of freedom, it tells you the shape of the t. So you can see as we go higher degrees of freedom, the t becomes more normal. So this t has 24 degrees of freedom, meaning if it was a one sample t, it came from a sample of 25. N minus 1 is the formula for degrees of freedom. You then click between for confidence intervals, and we enter in 95, and I was close enough to the right answer. Now, the reason I knew it was close to this answer is because as the t gets more degrees of freedom, it goes towards the z-score of 1.96. And I've done this enough that I can kind of guess it. 99% confidence with 92 degrees of freedom, simply entering 92, and this will approach 2.5758. It's not quite, oh, wow, they were really nice. I was on the edge of the right answer on this one, barely got it. But with 92 degrees of freedom and 99% confidence, the answer is 2.63. As I said, it'll go to 2.5758. As we increase the number right here, you can see it go towards 2.5758, which is the actual z-score. So t's get closer to z-scores as they go towards infinite degrees of freedom, because the t is basically the z more calculated accurately for when you're using the mean. Mr. T is mean if you're doing drugs. So let's look at a study of the annual compensation rates. Let's do that question. Tell me as many as you want, Peyton, and we'll get them done. Here it is. This one shouldn't be on this quiz. Kind of. Not a big fan of this one on this quiz. I should tell Terry. I'm like, we need to redo all these quizzes. Update the class. Okay, here we go. Chapter 14. This is kind of a reviewish question. A study of the annual compensation rate. So in this one right here, we're going to look at the mean and the standard deviation of samples of certain sizes. So if you look right here, we have the mean for a sample size of 30 and the standard deviation for a sample size of 30. So what we would know is when you do this, the mean stays the same. The mean stays the same. So the formula for this one right here is just mu y bar equals mu. So literally, all of these are mu. Does that make sense, Peyton? All of those are going to be mu. This second one right here is a little more complicated. It's going to be the standard deviation of y bar is equal to sigma over square root of n. And so all we're going to do is change n because this one's for 30. So we take the original standard deviation, divide by square root of 30. And so on we do, this one's going to be square root of 50. These numbers are just going to change over here what you divide by. So we'll do that right here, just solving each through. So the mean is right there, the mean standard deviation respectively. So the mean is 10,696.39. We just copy that down because the mean doesn't change. And the standard deviation is 17834.49. We have to take that number and take 30 and square root. And there it is right there. So we take 17834.49, divide by that, and there's this. And then we take 50 square root and divide 17834.49, divide by. And there's that. What's the next question, Peyton? We've almost got this one done because it's just s over square root of n. And then we take one. This one, you just move the decimal. 1783.45. And then we go right here. And 200, which is 14.4. I've done that a few times. And then 17834.49 divided by that. And there's the new standard deviation. And there it is right there. And we round. And in 1998, the campaign, is it the Chips Ahoy one? These values are probably pretty close to the values. If you look right here, they are all pretty close. Simulations do show realities. So they're, excuse me. Excuse me. Reasonably close to. And they are reasonably close. And we got the 100. Got the 100. Okay, let's do this one. This one's really easy with Excel. This one's a really good question. I do like this one a lot. Okay. We have, at the time of 823, Stat 201, Chapter 14, in 1998, as an advertising company campaign. Okay, so we have this campaign right here. They collected data on Chips Ahoy chips bags, and they saw how many chips were in there. They actually took apart each cookie and counted the chips. So in the first bag, they counted 1,132 chips, and they counted a lot. No, that was Chips Ahoy, especially in that bag. You know what's better than Chips Ahoy? Scoops Ahoy. If you know, you know. Stranger Things. So with that, check the assumptions. We need to randomly take the bags of chips. We need to take less than 10% of all bags, and we need the data to be nearly normal. That is the third condition right now for quantitative data. Always remember the first two are random, 10%, then you pause and you think towards what the third one is. Are we dealing with categorical, success, failure, which we're not, or are we dealing with quantitative, nearly normal? And they kind of state that here. They do all right. The data from a random sample, so they're just checking independence, which is random. The data from a random sample, so we can assume they're independent. Good. 10% has nothing to do with randomness. The data from our sample, they are independent. Whoops. And now we have to make the histogram right here. What's up, Liz? Good to see you here. I believe the histogram is going to be between these two ones. It's pretty hard, but we can actually narrow it down pretty well by looking at it. So if you see, how many observations are there between 1,100 and 1,200? 1, 2, 3, 4, 5. Okay. So 1, 2, 3, 4. So I think it's this one. 1, 2, 3, 4. And then there should be 5 that are around 1,200, or in the 1,200s. So in the 1,200s, there's 1, 2, 3, 4, 5. Yep. Payne, did you get what I'm doing? Liz, did you see how I did it? Is that I'm counting how many observations there are. It is this one right here, because you can count the observations, because you can look at the height of the bin and say that there should be 1 in the 1,000s. And you look right here and you find the 1 in the 1,000s. So yeah, good work. And Liz, if you have a question too, let us know the next one you want to work on. This one's a bit weird. It's asking about the nearly normal condition. It's basically unimodal symmetric. So because of that, it should follow the normal. We use the student t to find the p-value, but we're saying it should be nearly normal. This goes to the nearly normal condition. This is where we're going to jump in and use Excel. So we're going to go here to copy to clipboard. And we're going to copy it with Control-C. We're going to blank the screen real quick and open up Excel. Excel. Okay. We'll go over here. Okay. What? There we go. Pasted in. Data's now been pasted into Excel. I'm working on the data analytics summit now. Yeah, let me know about your interpretations. Yeah. And then we have the data pasted in. We go to data. We go to data analytics. Data analytics. Go to descriptive statistics. Click OK. Put your input range as the full vector, the full column. There's no label in the first row. That means like you put something like tornadoes or chips or something like that. That is not what's right there. And we go these two summary statistics and confidence intervals, and we click OK, and I go to a new sheet. And here's the answer right there. You see the 58. So the lower and the upper, they shouldn't call this confidence 95. They should call it margin of error. So our margin of error. So that's the margin of error. So the lower is going to be the mean minus the margin of error. And the upper is going to be the mean plus the margin of error. There's the answers. So know that this is the margin of error. That's very important for your Excel output. But the margin of error is down there at the bottom. And then the formula is basically, when you think about it, the formula is y bar, which this is y bar. That's standard error y bar. That's the median, the mode. The standard deviation is S. Sample variance is S squared. Kurtosis, those measures don't matter. This is max minus min. The range, oh, that's the range. That's range. Min, max, sum of the y values, count is n, and margin of error. Good to see you, Reptar, in the chat. And y bar plus or minus the margin of error gives you the lower and the upper. So that's where it is. Yeah. And I wonder if I can just copy this. Let's try it. Yeah, look at that. It should work. I didn't know if that would work. And it did. I believe it did. 1 decimal, so watch out. This is where you lose points. If you were to lose these points, please email me and be like, Brian, I didn't round. Don't worry, I don't round sometimes too. So what this means is we are 95% confident. This might help out Liz right here. We are 95% confident the true mean chips in the bags is contained in the interval 1182.4 to 1298.6. So it looks like there's evidence the true mean is greater than 1,000, but we don't know that each bag, because each bag is different. That's an individual bag, might have less than 1,000. One bag was kind of close-ish, but there's evidence the true mean is greater than. Because the interval is entirely above 1,000, the mean number of chips per bags is likely more than this. However, the normal predicts a small amount of individual bags. Should be right. Yo, we did it. Does that make sense, Peyton? This is a really good question. It's one of my favorite ones. Because you got to know the conditions. Random, 10%, nearly normal. You should know how to look at a histogram to evaluate it and see which one's right. You should know how to put data into Excel to get a confidence interval and know what the confidence interval means. I'm 95% confident the true mean chips per bag is contained in the interval blank to blank. It's a really good question. What should we do next? This is very similar to the one we just did. That's almost identical. This is the one that was mine. Based on meteorological reports. Let's go find it. And anyone can put any questions in the chat if you want. Here we go. Ooh, it's an interpretation one. So, 1503. Based on meteorological. Okay. Based on meteorological data, the news station usually forecasts an average of 22 inches plus or minus 4 inches. So what you want to immediately do right here is you want to write the interval. If you get information like this, this is their average forecast. Y bar is 22. Margin of error is equal to 4. The interval itself from lower to upper is y bar plus or minus 22, which I should have put in what y bar was then. So it's, y bar plus or minus margin of error, where y bar is 22 and the margin of error is 4. So the interval is going to go from 18 to 26. You just add and subtract margin of error. That's how we get the interval. So now we know the interval is 18 to 26. We want to interpret it. So how do we interpret it? I'm going to put confidence in the chat, and Mubot's going to put what the confidence interval interpretation is. And it is, I am 95% confident that the true mean average snowfall in this town is contained in the interval 18 to 26. Now notice, the middle is the hard part for people, the true mean average snowfall. So let's think about this. With what I just said there, during 95% of the past 100 winters, they got between this and this. What do you think is the right answer? A, B, C, or D, Peyton? What do you think? Is the interval about 95 out of the last 100 winters, they got between 18 to 26. Is that what it is? That's the 4-part. Nice job, Liz. Yeah, I am blank percent confident that the true blank is contained in the interval blank to blank. And the first one will be true proportion on your assignment. The second one will be true mean of, make sure to give the context, like true proportion of days that are high demand or something like that. You know what I'm saying? So that's the second part, is the context, like how confident you are that, yeah. You're welcome, Liz. Good question. Great timing that Peyton chose this one. And good job looking over the assignment and understanding that's the 4-part interpretation right there. Got 4 blanks. So which of these look correct? A, B, C, or D? Well, this is wrong because it's not about past winters. So it's not about next winter. It's right here. The intervals for the population mean of snowfall, not for individual winters. I am this percent confident that the true, which is for a population. There's a 95% chance that the region will get between this and this snowfall this winter. No. The interval is made to understand the truth. The interval is for the population mean, not for predicting the individual winter. There is between 8 to 26 inches of snow on the ground for 90% of winter days. No. It's about the average snowfall of winter, not of winter days. The interval only estimates, no, the interval is for predicting the average snowfall for not just next winter. It looks like this one. Yeah, it could predict next winter, but it should be predicting future winters or something. Don't love how they wrote that. Residents can be 95% sure that the area's average snowfall is between this and this. That actually might be right. I am 95% confident the area's average snowfall is between this and this. That looks correct. I hope I don't get that wrong. Residents can be, residents can be 95% confident the average snowfall during the past century. No, it's not about the past century. We know what the past century was. It was 22 inches. Oh, it's not this one, is it? It's not that one. Where did I mess it up? Where did I do wrong? Oh, I haven't gotten one of these wrong in a long time. Okay, it's this one. Okay. The interval is predicting the average snowfall for, like I said, that was the one I said no. The interval was based on a sample of snowfalls for several years, not the amount of snow on the ground for a sample of days. The confidence interval only estimates what happens in the years in the sample. No, it's got to be this one then. Yeah. For the, he just gives a general one. The confidence interval was based on a sample of snowfalls from several years. That's a fact. Not the amount of snow on ground for a sample of days. That's true. Remember I said it's not about predicting next. It could predict next winter. No, it's not really. Yeah, I misspoke. I mean, it's about the true average snowfall. That's what it predicts. It doesn't predict next winter. I should have caught myself on that one. I was like, well, it's not really that. Should have read the other ones more intensely. A researcher investigates whether the mean cholesterol level among those eating frozen pizza is this. Let's check that one out. I got one wrong, Peyton. We got to throw the 50,000 points of office hours for this. For Brian getting one wrong, we're dropping 50,000 points. I can't even type. It's okay. Still W. Thank you so much. We all make mistakes. And everybody hurts sometimes. Where is it? W Raptor. Where's the pizza question? Here it is. Pizza question. Pizza time. 2043 Statue 1 chapter 14. A researcher investigates. Okay. Pizza. The confidence interval. Well, let's look at it. The confidence interval. Okay, double. Yeah, let's do that one. We'll do. Ooh, the speed of light one is crazy. That one has a lot of decimals. Ooh. Okay, we'll do that one here next. So the confidence interval goes from this to this, and if you have above 220, that's risk. So the interval is saying we think the true mean cholesterol level for people who eat frozen pizza, probably a lot. It's not bad if you eat one frozen pizza. Is contained in the interval 226 to 243. So the interval is entirely above. So this is evidence of sufficient risk because we have evidence that the true mean is higher than this because we're confident, 95% confident, that the true mean is greater. They didn't give a confidence level. They should have. So really quick question right there. But the interval gives possible values of the truth. We believe that the truth is higher than what they're thinking it might be. So you would reject this value. If you did a statistical test, you would reject it with a p-value less than 0.05, as long as this is a 95% confidence interval. Then you do not. If 220 is being tested, you would not reject that, Peyton. The interval contains it, so there is not sufficient evidence to reject it if it's 220 being tested. Does that make sense? So if yours has 220, like Peyton's right there, then do not reject it, because 220 is a plausible value, and we would not reject the value. There is not sufficient evidence to reject 220 at that point. Good question. This one is a decimal place nightmare, so have your calculators ready, because this one carries a lot of decimals with it. Okay, here, 22, 23, and we need more questions. Drop questions. Reptar, Liz, drop any questions you got. Chapter 14. In 1882. This is before the t-test. Michelin star guy. I'm going to show my wife. I'm Zoom question guy. It's a Rick and Morty reference where he's like, I'm such and such guy. I do the such and such thing. If you're in class today. Luckily, a few people got a laugh out of that. I do things to crack myself up sometimes, and then to show my wife later. Why do you teach, Brian? To make my wife laugh. Find a 90% confidence interval right here, so we have to know how to write the confidence interval and do the work. So one of the biggest things when it comes to test 3 is your notation. Who can tell me any notation from this problem? And what they did is they took off this 299 just to make the math easier. You have to add it back on at the end, if I remember correctly. So just do it without the 299 on it to start. Because I think they leave it off. We'll double check. Any notation. Any notation. Any notation. Not Zoom guy. Thank you, Peyton. Peyton was in class. I'm Zoom guy. Any notation. Any notation. Awesome, Liz. Have a great day. Good work. Standard deviation and mute. Yep. This is standard deviation. This is... but that's not mu, though. That's sample mean, because he took samples, took 23. So that is going to be Y bar. Good answers right there. That's Y bar, though, because it's the sample mean. He doesn't know the true speed of light. He has samples of the speed of light. So we have estimates. That's why we estimate the speed of light. We don't know the speed of light. We just have estimates of the speed of light. So, like, what is the true speed of light? Probably close to this. So we're going to make a 90% confidence interval to estimate the true speed of light. So there is one more notation, and it is degrees of freedom right now. Degrees of freedom are 22, because right now the degrees of freedom formula for the one sample t is n minus 1. So that's the important thing to know. One sample t, which means you're doing one mean. One sample t is n minus 1 degrees of freedom. And so what you need to do now is you need to go to your t-table, and you need to look up the proper t-value for 23 degrees of freedom. 23 degrees of freedom, 90% confidence. The t-score is 1.7139. So you need to make sure you have the right t-value related to your degrees of freedom, which is n minus 1 sample size for the one sample t. So 24 sample size, 23 degrees of freedom. And then make sure you put in between and have find t using p-value and have 90% of the area. 1.7139. So that is a t with 22 and 0.05, 0.95, we'll put 0.95 equals. Did I put 22 or 23? I knew I did. So 7171. Very similar to the z-score. It'll be used in this interval. So now the formula is going to be, you know what, I wonder if I could do this. The formula is y bar plus or minus t star and then s over square root of n. So this is going to be y bar is equal to the sample mean, right? 756.216 plus or minus, and then t 1.717, and then s or square root of n, square root. This is making sense, Peyton? This is the fun problem because of the decimals. 107.119. There we go. Here we go. Ah! Biggest calculator ever. And I always solve this part first, which is the standard error. So when you're solving this, solve this first right here and then multiply by the t for the margin of error. So 107.119. Well, that was fun. 23 square root 107.119 divided by that, 2233. So that's the standard error. What we found right now is this quantity. Multiplying by this gives us the margin of error. And so now that's the margin of error right there. So the margin of error is 38.35. And then we simply add and subtract it to this. So we're going to take 756,216, and let's go plus this. There it is, 794. And actually, let's 79456. And now what we can do is we can minus that number, and that brings us back to the mean, and the mean minus this. So all I did was minus. So if you're wondering, it's just, I just subtracted that value of like 36, like 756 minus 36 or something, or 38 or whatever it was. There it is, 38. So 756 minus this value is the lower, 71786. And I believe, let's make sure we got the decimals. There we go. 2 decimals, and I think you have to add on the 299. Yeah, because it's saying the true speed of light. It's not, you have to add that back on. They really make that confusing. In other words, what does this mean? We are 90% confident that the true mean speed of light is contained in the interval. Then the confidence interval, what is the 90% confidence? What does the 90% confidence interval mean? The confidence interval contains the true speed of light 90% of the time. With 90% confidence based on this, the speed of light is between the lower and the upper bound. Yes. The confidence interval. Not that this interval, it's about repeated. That's more the theory. What assumptions have to be made? It's not that it follows a uniform. The sample is drawn from a large, no. The measurements arise from a random sample or suitabilized random experiment. They're independent. And I think that's got it. Whoo-wee! Yeah, the Pearson wording. The top one is almost correct. It's more for the theory that it's not that this interval contains the truth 90% of the time. It's that repeated creations of 90% confidence intervals contain the truth 90% of the time. So 90% confidence intervals contain the truth 90% of the time, but I am 90% confident that the true mean speed of light is contained between the lower and the upper. Yeah. What's another one? What's another one? Another question. Why am I so tired? Oh, let me see. Oh, should be live. I'm going to send someone the link here. They said they couldn't find the link. There we go. There you go. Yep. You're finished? Nice job, Peyton. Okay, we may have another person joining in. Those are some of the hardest questions. Maybe we'll put easy questions now. Did you get 100? You can say. Have you done? Yeah. Do you want to do the homework, Maddie? Let's do the full homework. How's that sound? We've done it, but let's do it, right? Let's do the full homework. I think I'm having Red Bull withdrawal. It's real. Man, I'm like, I want some Red Bull. I don't want Red Bull. I need it. If someone stood at my door right now with a Red Bull, I'd be like, shh, shh. All right, I'm going to get a soda. I'm not going to get Red Bull between this. I'm getting a soda. Soda. Something sweet. 7-Up. Squirt. Squirt. I'll just drink sugar instead. I had another feeling. I'll drink some sugar. That's good for you too, right? Trade one addiction for another. That's what we do here. Don't do that. Be smart. Smarter than Brian. It's the way to be. It's the way to live. Okay. I'm getting a little smarter every day. More smarter. I'll be most smartest soon. Okay. Chapter 14. Homework. Where's that? Confidence interval. Okay, Maddie, here we go. Let's get some hundreds. These are my absolute favorite questions. My absolute favorite questions. Who knows the answer to this one? 90% confidence interval with degrees of freedom 20. You have to go to the T-applet. See if you can solve it right now. Then I'll show you how to get the answer. But I love guessing these. 90% confident, 20 degrees of freedom. The answer is going to be close to about 1.78. Don't tell me I can guess it before you can get it. I only get 2 guesses. A little further out, really? Is it? Is it? Is it, Peyton? Between. There we go, 1.72. Good work, good work. I'll shout it. And good to see you, John, and everyone. I think that's going to have it right there. Yeah, good work. Don't worry if you got it wrong. Don't worry if you got it right. 1.72. Here's how to do it. Go to the T applet. And so you need... I seriously thought there was going to be a Red Bull delivery. Don't bring me a Red Bull. Go to 20 degrees of freedom. Find the T using a p-value. 90% between right here. And there it is. Does that make sense? So we got that one right there. Make sure to go to the T applet. There it is right there. So there it is. 98%. I need to be like, Mom, give me a Red Bull. 98% confident with 78 degrees of freedom. I can guess this one. The reason I know this is because I know the z-score of 2.3263. And so I go and in my brain, what was it, degrees of freedom there? 78 degrees of freedom. So 78 degrees of freedom, 98% confident. It looks like this right here. And I was close. I was off by 200ths. But as you keep going to more degrees of freedom, it's going to approach 2.3263. So as you go up in the degrees of freedom, it approaches the z-score of 2.3263. So there it is. There's 2.3263. And it's just, after you get past 100, the differences are very negligible. Does that, who thinks they understand that T's and Z's are very similar? T's are more exactly calculated and the differences are bigger for smaller degrees of freedom. Does that make sense in the chat? T's and Z's are very similar. A T is a more exact calculation created by William Gossett, used for the mean. You use degrees of freedom to tell you which T you're using. And as there's more degrees of freedom, the T and the Z converge towards the same answer. So that's why when someone's like, tell me, don't use the applet. With 200 degrees of freedom, what is the 95% confidence interval T score? With 200 degrees of freedom, what is the 95% confidence interval T score? Don't use the applet. With 200 degrees of freedom, what is the T score we would use? For 95% confidence. If you know the trick I'm telling you, then you'd be like, well, it's probably about this. With 200 degrees of freedom, what's the 95% confidence interval T score? Well, that's a lot of freedom, right? So with a lot of freedom, the curve is basically the normal curve. So the answer is almost, but not quite 1.96. It's probably 1.97. Does that make sense? And if you keep going up in the degrees of freedom, it'll go towards 1.96. 1.95996. Does that, who's like, okay. Yeah, just a tiny, does that make sense, John? Like, after about 100, it's pretty negligible. It's meant more for because at 100 degrees of freedom, it's probably 1.98 or so. The differences are very small. It's really when you're down towards 20 degrees of freedom, or 10 degrees of freedom, or 5 degrees of freedom, or 2. At 2 degrees of freedom, the 95% confidence interval is very different. At 3 or at 1. It's meant for small degrees of freedom that you see the biggest differences. As you go towards higher degrees of freedom, it's at 60, it crosses over the 2. So it's very easy to remember at 60 degrees of freedom, it's actually 2, like the 68-95 rule. It's actually 2 at 60 degrees of freedom. So I hope that kind of helps out, John, on why we do that. And that kind of answers this question here, number 2. What's the deal? What happens to the T as it gets more degrees of freedom is A, B, C, D. As the T gets more degrees of freedom, what happens to it? As the T gets more degrees of freedom, what happens to it? Nice job, John. I'm going to throw everyone another 50,000 points. We gave one out earlier, but we got more people here now. So what happens? We got a good question in the chat. We might have, I think we did that one earlier, Peyton. Check out researchers measured. Did we not do that one yet? Might be able to do it. I just see 500,000. Whoops. Well, you were here for it. Is it A, B, C, or D? I did put an extra 0. As degrees of freedom increase, what happens? What happens? We can see it. Uh-huh. The spread becomes, it does narrow, right? It gets less spread out. Mm-hmm. Yep. Thank you. I had to double think. The reason being, and you can see it with the applet, if you go to 1 degree of freedom and you look at the scale at the bottom, you see how it's spread out across -10 and 10. As you increase degrees of freedom, it starts to get less spread out and goes across a smaller interval. So as degrees of freedom get bigger, the t gets more narrow and goes towards the normal. So just very important to know that t approximates the normal with higher degrees of freedom. We'll do all these really quick right here, and then Peyton, we'll do your question. You got it, Peyton. We're gonna do the full homework, and then we'll loop back to that question. Then we'll run off. Chapter 14, homework, question 3. You can do it too. The housing market has slowly recovered since the 2008 financial crisis. Recently, in one community, many retailers sampled 49, which is the sample size, bids from potential buyers. They showed an average loss of 9,142 with a standard deviation of 1566. Complete parts A and B. What do we need to check? Random, 10%, and then what's the third condition? Is it C? I bet you're right. Because success failures for categorical data, this is not categorical, it's quantitative. So we're not doing that. And I think you're right, it's probably this. We're going to see independent and random. For independence, use the randomization condition. That sounds right. And check the normal. Now make your 90% confidence interval.
Notation, brother.
Notation, brother. So with this, let's jump into the notation. Here we are, writing our notation. Tell me the one thing of notation I forgot to write down. It's not given here, but what is the one thing of notation that I need to add to this? Who can tell me? Because I'm about to use it. I'll write the number, and you tell me what it is. There's one bit of notation I'm missing right now. Oh my gosh. The degrees of freedom, which tell us which t we're using. All those degrees of freedom in the chat. And so the reason we need the degrees of freedom is because it's n-1 degrees of freedom down here. This is where the degrees of freedom go. You do not multiply by it. But that tells us which t we're using. So there's 48 degrees of freedom. They want a 90%. So that's going to be about 1.68 or so. We go back to our applet. So 48 degrees of freedom with 90% confidence. 48, 90% confidence. There we go. Between. There we go. I got it. 1.68. I'd maybe carry these decimals. 1.6772. And we go back over here. 1.6772. And then we throw in the standard deviation of 1566 over square root of 49 times by plus or minus. The y bar is 9142. And so let's clear out here. 49, that's 7. That's cool. Square root of 49, everyone knows that. And 1566 divided by 7. And then times 1.6772. And then we just add and subtract. That's the margin of error right there. So 9142 plus or minus this. So 9142 plus this, 9517. And then we go minus. So we're taking 9142 minus. This is the formula right here. We're just doing the mean minus the margin of error. And can we copy 8767? I think we've done it correctly. Yay! Good question. Very good question. Okie dokie. Well, let's do this one right here. The housing market has slowly recovered. We did this one. Wait, sounds just like what we just did. I suppose the standard deviation of losses had been 3,000 instead of this. What would the larger standard deviation do to the width of the interval? Well, we can figure that out. If you look at a bigger standard deviation, it'll do what to the interval? If standard deviation got bigger, then what would happen to the margin of error, which controls the width of the interval? If standard deviation got bigger, then the margin of error would do what? If there's more variation in the data, variation is like this. This is more variation. This is less variation. It'd become Peyton. A larger standard deviation increases the width of the confidence interval. It's more variation in your data. A classmate suggests that we reduce the confidence level to 90 instead of 95. What do I need to agree with them on? That they say, classmates suggest that the margin of error in the interval could be reduced if you changed to 90 to 95. So 95, 90, are they right that it would reduce the margin of error when you go to 95 to 90? Because it goes 68, 95, 99.7. So if you go 95 to 90, are they right? Are they right? I would say yeah. Because if you go to less confident, it's because 68, 95. So does that make sense? You remember, Maddie, when we go like 68, 95, 99.7? So when you go inwards, yep, we did it yesterday, Braden. Yep, check out yesterday's and let me know if you have questions. I can do it probably quicker, but I don't know. I did a lot of explaining. Yesterday's office hours have a full walkthrough of it. Good questions. So when you go 68, 95, 99.7, your hands go out. So if you were to like go 95, 90, your hands would go in and you'd have a narrower interval. Yay! Did it help you, Peyton? I hope it helped out. Instead of changing the confidence level, would it be more statistically appropriate to draw a bigger sample? Yes. A larger sample would reduce the margin of error. There we go. It would reduce the standard error. It's talking about this component over here, that if you were to take a bigger sample, well, we should do a different color. If you were to take a bigger sample, it would reduce the standard error, which the standard error would then reduce the margin of error. So, yeah, awesome, Braden. And that seems appropriate right there. Yay! Easy one. Who's got it? A, B, C, D. Easy one. Sample size 15, one sample T. What's the degrees of freedom? You get a question like this on the test, you're like, yes. Yes. It is 14. It's n minus 1. So it's just n minus 1 for the one sample T. Nice and easy way to remember it. One sample T, n minus 1. Great job, Maddie and everyone in Peyton. Excellent work. Here we go with the next one. Livestock. We're going to do some interpretations here. First thing we want to do is we want to know how to interpret this appropriately. Now notice it's a confidence interval for the true mean. So I am 95% confident that the true mean weight of these livestock that they will gain is contained in the interval 66 to 88. That's because the interval is 77 plus or minus 11. So minus 11 is 66 and plus 11 is 88. So I am 95% confident that the true mean weight gain of these livestock is contained in the interval. 56 was the average. Whoops. The interval goes 56 minus 11, 45 to 67. So that is the interval right there, 45 to 67. I am 95% confident the true mean weight gain. 95% of the cows studied. No, it's not about the cows studied. It's about the true mean weight gain of all the cows. So the confidence interval is for a population mean, not about the cows in the study, because we're trying to estimate the true mean weight gain. I just want you to think about this. Like, I think I'm always hungry. Thanksgiving's coming up. Oh, man. Oh, man. Okay, your mom. Copy an image right here. Your mom makes this sauce for Thanksgiving turkey. So you go and you take a spoon and you take a spoon of the sauce and you try it. You've just whatted the sauce. Turkey gravy right here. You've taken a what of the sauce. You've taken a what of it. You go in, you go. Taking a what? You're taking a sample. Now, have you tried all the sauce? Have you tried every bit of that sauce? No. You are sampling the sauce to make an inference about all the sauce. Does that make sense? When you say to your mom, the sauce is good, you're trying to tell her that whole sauce, not just the sauce you tried. If your mom says, you haven't tried all the sauce, you'd be like, you gave me a representative sample of the sauce, and I have used my sauce to make an interpretation about all the sauce. So that's what we do in statistics is we take a sample to try to understand the population, to have a guess or an estimate about the truth. So when you look at this, it says one is 95% sure that a cow fed. No. We're trying to estimate all cows. Like, what is the truth for every single cow? So this is wrong because the confidence interval is trying to figure out the truth for all cows. The confidence interval is not for individual cows, it's about all cows. One is 95% sure that the average weight gain among the cows in the study. No, we know the cows in the study gained 56 pounds. So it's incorrect. We don't know the weight gain of all cows. We only know the weight gain of the cows in the study. That's Y bar. The average weight gain of a cow fed this supplement will be between this 95% of the time. No, it's not a singular cow. The confidence interval estimates the weight gain. No, the average weight gain of all cows does not vary. It's a constant value. That sounds about right. I don't like that one as much. If the supplement is tested on another sample of cows, there's a 95% chance that the average weight gain will be between this and this. Nope. There's a 95% chance probability that it'll be within 2 standard deviations of the true mean. Notice this says true proportion. We're not dealing with proportions. We're dealing with quantitative data, so it's the mean. Oh, yeah, sure. Yeah, Brayden, could do that one here. We got, I think, 2 more. And then, did I mark that one? I marked that one. Okay, and then we'll do those 2 questions. Brayden, you got it. They got to run. 4803, stat 201. Chapter 14, homework, question 7. A biology class looks at the birds and figures out that on average there's 16.34 to 18.69 birds species seen. Someone gets mad and says, well, you can't do singular species of birds. There's either 16, 17, or 18. That's not what an average is. On average, families have 2.3 kids. Doesn't mean there's a 0.3 kid. I mean, I might be that 0.3 kid, whatever that means. But that's not how things work. So the mean can be decimals. Yeah. The confidence interval estimates the true mean, not the sample mean. The confidence interval is trying to estimate the true mean. And the true mean can have decimals. Brayden, let's do that question. Woo! It's p-value going on to the alpha. Boy. I'm just going to take a nap in the chair. Chapter 14 quiz. You're welcome. You're welcome, Maddie. I bet it'll help a lot of people. It's a good question. Here we go. Which of the following is true about the T? I think it's back here. I think it's like 3 or 2. How'd I know that? Okay. I didn't just say that because I was about to click. I was like, I think it is. I remember being it back here. And 49, 33. Done these questions a few times. Let's think about this. Okay, which of the following are true about the T? As the degrees of freedom, increase, the T becomes more normal. Type T or F in the chat. As degrees of freedom increase, the T goes towards the normal. I'm increasing degrees of freedom. True or false? So as there's low degrees of freedom, here's increasing degrees of freedom. As degrees of freedom increase, the T goes towards the normal. Very true. Totally true. The T is unimodal and symmetric. True or false? There's the T. Is it unimodal, one peak, symmetric? T or F? True. I've been on Top Chat this whole time. What's wrong with me? It's true. The T distribution has fatter tails and a narrower center. That's easier to see. It's true. That's easier to see at low degrees of freedom. At low degrees of freedom, you can see the fatter tails, as in there's more area in the tails. You see it's out towards -5, which the normal curve doesn't usually have area out towards -5. Hence why as it approaches the normal, you'll see the area start to go inward. The number line changes, and there's not area like that. So the T curve, and it's more narrow in the center, like at low degrees of freedom. It should be like at low degrees of freedom, the T has more area in the tails, and yeah. I think the waist size question was here now. I'm on a sugar high. Waist size. Okay, let's do the waist. We're going to do the waist size question. I'm going to go on a run, get some energy. I'm the go on a run, get energy guy. I go on run and get energy. Chapter 14 quiz. I amuse myself. Researchers measured waist sizes. Once again, these, don't worry. We already did one. Peyton knows. Both Peytons know. These are kind of misplaced, in my opinion, here. Because this is sampling distribution of the sample mean, which has relevancy to topics we're talking about. But what they want you to do is to find the theoretical mean and the theoretical standard deviation for certain sample sizes. What this means is the mean is equal to mu y bar is equal to mu. So each one of these is equal to mu. Whatever mu is, they shall be. The standard deviation for these is simply going to be the standard deviation of y bar is equal to sigma over square root of n. It is sigma technically. Exactly, it stays the same exactly. So what you'll have to change in these is you'll have to take sigma and divide by square root of 2 and change it to square root of 5 and such as you go down. So for the first one right here, the mean is going to stay the same for all of these. So the mean waist size is 36.344, and that's going to stay the same for every single one of these. The standard deviation of 4.027 is going to change by a square root of 2, as divide by we mean. So we go 4.027, divide by that, 2.85, or 2.848. Next, we divide by square root of 5, so 5 square root, and then we take 4.027, divide by square root of 5, and we get 1.801. Then we take 10, I think it's like 3.13. What's 10 square root? Oh, it's close, 3.16. So 4.027 divided by this. Hey, Charlie, good to see you there. Something seems odd. 4.027 divided by this. There we go. It got way too small, way too quick. 1.273. And then square root of 20. Is it? There it is. And then we take 4.027 divided by square root of 20. And we get 0.901. There we go. And the theoretical values are actually very close. It has them down here in the table. We can check the values, but if you notice, they should be kind of close. That one's a little more off than I like, but I'm going to say it's close enough. Let's hopefully don't get that one wrong. They should be reasonably close and reasonably close because these are simulations. Use the sample size. Oh, ooh. Charlie, if you want to email me on that, I'll check real quick. For my chapter 14 quiz on Canvas, this is Talent Handbook. Pearson says did not do it. Let me know because of all the gradebook things, because you might have done it earlier or something. Let me know, because I've been having to fix up the gradebook. I think we only need 5 because it's not that skewed. So use a sample size of 5 since this is the smallest when the distribution is unimodal and symmetric. And what about the shape? Determine that we only have to use 5. The distribution is very unimodal symmetric mostly. So the sampling distribution sample mean doesn't need to have that large of a sample size. Oh my gosh, what I miss. Is it 10? It's not 10. What did I do? Oh, is it this one? Oh my gosh, I bet it is. It is. I did the first thing. I even called that out. Last question of the day. Wait, what? It's 2. Wait, it's not that one. Where is it? Not that one. It's this one? Okay. Brian can't math. 4.027. Oh, no way. I entered in this. What did I have? I had this in. And it's this. I literally was off by 1,000ths. I was off by 1,000ths. 50,000 points. I would be, if I was a student, I'd be like, yeah, be kidding me. 1,000ths, because I rounded that up, which you shouldn't do. Wait, This rounds up to round up this, to round up this, to round up this, to round up this. You keep rounding, it rounds. But if you don't round here, if you're around there, it depends on where you round. Numbers aren't real. With that, bye for now, everyone. Bye.